Okay, today we are going to be talking about data compression. We will begin with what the idea behind file compression is, and then we are going to talk about Huffman tries, which is a way of doing data compression. Okay, and we are going to see how abracadabra translates into the sequence of zeros and ones, right. So, what is file compression? So, text is usually stored as if you have a piece of text, it is stored as bits in your computer, right. And what is typically done is that for each character you have a what is called an ASCII code, right. So, if you were to go into a Unix shell and type man ASCII, then that will give you the ASCII code for all the various characters, right. The ASCII code is an 8-bit code, which means that for every character is stored as 8 bits. Okay. So, this is what is called a fixed length encoding. Why fixed length? Well, because for each character I have the same number of bits. Yeah. But our idea today is to try and reduce the amount of space required to encode a piece of text, to maintain a piece of text, to keep a piece of text, right. So, if for each character I am going to use 8 bits, then the total number of bits required will be 8 times the number of characters in that piece of text, right. But suppose I do not have to do fixed length encoding. Suppose I decide that some characters might have 2 bits associated with them, some characters will be encoded using 3 bits, some using 4, and so on and on. Can we exploit this, right? And the fact that some characters occur more frequently than others to design a coding scheme which will represent the same piece of text in lesser number of bits, using lesser number of bits. Right. You understand the need for doing this kind of compression, right. Clearly, the lesser memory you require, if you are transmitting the file, you will have to send less number of bits. If you are storing, you will have to store less number of bits, and so on and on. So, it is very useful to be able to compress the information that you have. Okay. So, that will bring us to what we call variable length encoding. So, the number of bits used to represent each character would be different. In particular, characters which occur more frequently, we are going to represent them using more or less number of bits? Less number of bits. We will take some small number of bits and use that. Okay. And characters which appear very infrequently, let us say X or Z in the English alphabet, for them we can have longer sequences, maybe more than 8 bits even. Okay. Let us see how this is done. So, let us say my piece of text is just 4 characters Java, okay, and I decide to encode A. So, how many characters are there? Suppose my alphabet was just A, J and V, right. Suppose this was my entire alphabet. The only things that I ever encoded were strings on this alphabet A, J and V. So, Java is one example of such a string, and suppose I were doing fixed length encoding. How many bits should I associate with each of these? I will need at least 2, I can't do with just 1, right, because there are 3 different characters and there are only 2 possible values if I chose 1 bit. So, I need at least 2 bits, and if I take 2 bits, then how many bits do I need to represent Java? 2 times 4, 8, as straightforward as that. But suppose I decide to use 0, just a single bit for A, and 1 1 for J and 1 0 for V, and I will tell you why I am doing this, right. So, then Java can be encoded as 1 1 0 1 0 0, right. That would be the encoding, and it will take only 6 bits, right. It will take lesser number of bits. So, then you can ask me, well, why did I do J as 1 1 and V as 1 0? I cannot start with 0, but why do not I have J equals 1 and V equals 1 0? Okay, let us see. So, the problem with variable length encoding is that of decoding. How do you decode? Given a sequence of bits, okay, you want to decode it uniquely into, so suppose I gave you this sequence of bits, then you should be able to retrieve Java from this. Yeah. I also of course told you what the codes were. You should be able to get back to Java. So, suppose for instance, I had used this as my encoding. Okay. For A I use 0, J is 0 1, V 0 0. So, still it should take 6 bits only, and the encoding would be 0 1, 0 0 0 and 0. Now, from here can I get back to Java given this code? So, well 0, 0 1, well what can it be? Can it could be either a A or it could be a J. Huh? Why it has to be a J? Because they are using this 1. Okay, चलिए मान लिया, पर इसके आगे क्या करेंगे? ये 4 zeros का मतलब क्या है? Right? It could be Java, it could be JVV, or it could be Java. Right? So, ambiguous. You see the problem, right? If you were to use variable length codes, then you could have this problem of ambiguity while decoding. So, you have to be careful when you are using variable length codes. This problem would not arise when you had fixed length codes. You understand why? Because you will take those many bits and then determine what exactly the character was. So, to prevent ambiguities in decoding, we will ensure that our encoding satisfies what is called the prefix rule, which is very simple. It says that no code is a prefix of another code. By code I mean the bits I use for a particular character. So, जैसे ये जब when this was our code, so you can see 0 was not a prefix of either J or V, and J and V were also not prefixes of each other. And so, the encoding arising out of this would be unambiguous, and we will see an example to show that, to illustrate that. But the encoding arising out of this will be ambiguous, right, because A is a prefix of these, right, and you will see as soon as I show you an example what I am trying to say, but you understand what the prefix rule is, right. So, if your code satisfies the prefix rule, then decoding will be unambiguous, but if it does not, then you will have ambiguities in your decoding. Okay. So, I will come back to the prefix rule in the next slide, but now a code, a set, so a code is the collection of code words. Okay. So, what I have written out here is a code, and each one of these is called a code word, right. So, for each character the sequence of bits is what is called the code word, and the entire thing is called a code. So, a code which satisfies the prefix rule can be represented as a tree, in particular as a trie. Okay. So, in this trie what we are going to have, so recall the trie that we had discussed in the last class, the branching was a 26-way branching, but here our branching will only be a 2-way branching. Each node will have only 2 children. Okay. And so, I have the characters. So, here my alphabet is A, B, C, D, R, 5 characters only. The characters will be stored at the leaves or the external nodes, okay. And for every node the left edge will be labeled with a 0 and the right edge will be labeled with a 1. Okay. Now, A equals 0 1 0 because if you look at this, as you from root to A you will encounter 0 1 0 from root to A, right. When you are coming to R, 0 1 1. So, code for R will be 0 1 1. Okay. Now, can you see that if I drew such a picture for you, then the code word for any character will not be a prefix of the code word of some other character, right. Otherwise, it would have ended midway, but it is not, because everything is a leaf. Each character corresponds to a leaf. That is the very first statement here, right. So, the code for one character, the code word for one character would not be a prefix of the code word for another character. Okay. Right. So, we will represent our codes using such a, we trace from the root to the particular leaf to determine the code word for each character. Okay? So, I need not have shown this picture at all, I could have just drawn this try, and from this you can figure out what is the code word corresponding to each one. Okay. Now, how do we do the decoding? So, suppose this is my try, right, these are the code words, this is the code, and now I give you a sequence of bits. Let us say this is my encoded text, and I have to decode this text, right, and as you can see the code satisfies the prefix rule. So, how do I do the decoding? Anyone? So, I start from the beginning, right, you always start from the beginning, right, you never start from the end. Okay. So, you start from the beginning 0 1 0, so you will trace out 0 1 0, you hit a leaf. So, you stop and these 3 characters go away and I get an A.
You start with the 4th character.
Right. So, I will write down an A. So, I have struck off these 3 and I have written down an A. Now, I will take 1 and the next one is also 1. So, I get a B and I will strike these 2 off, I have taken care of these 2. Now, I get a 0 1 1.
Abracadabra.
I get an R, sorry, it is 0 1 1. So, 0 remains. So, 0 1 0, 0 1 0, and as you can imagine it will come to the same abracadabra. Okay. Right. So, that is what this will turn out to be, and you can decode it and see. Yeah. Suppose I give you this try and I give you, so I just need to give you the try and I give you this encoded text. Huh? How much time does it take to decode?
Order of the length of the text. Height into order of the length of the text. Height into length.
Height into length?
No.
Order of bits only. Only the number of bits, right? With every bit, right? Clearly, I am just looking at a bit and how much time am I spending with every bit? 1 unit of time, right? I just look at that bit and go down 1 level in the tree, maybe. That's all. Right? So, it is basically length of which you have to spend clearly. Okay. So, this is another try, and you know, this is a long piece of encoded text and you can figure out what this is. I do not know, I have not figured it out myself. So, you can take this as an exercise. These slides are there on the website and you can, I think it is something Robert or some such thing. So, you will have to see what is happening. Okay. So, what is our aim in doing this, right? We wanted, recall, we wanted to build up a code in such a manner such that the total length of the encoding is as small as possible, right? So, suppose this was my code, this try was specifying my code, and once again I was encoding abracadabra, right. So, now this would be the code, you can check, this would be the encoded message and this has 29 bits in it, right. How will you compute such a thing? Well, let us quickly do that to make sure that you understand. So, what is the frequency of each character? How many times does A appear?
5 to 5.
5? 1, 2, 3, 4, 5. B?
2.
Twice. C? Once. D? Once. R? Twice. How many bits am I using for A?
3. You should use 2.
3. For B? 2. For C? 2. For D? 2. For R? 3. हाँ, तो ये multiplication समझ में आ रहा है मैंने क्यों किया? Right, I am just counting the number of bits, right? So, this becomes 15, 4, 2, 2, 6, 29. Yeah? Great. Now, suppose I had another try, this. Do you think this will have less or more?
Less.
Right? A was occurring 5 times. Here I was using 3 bits, I am using 2 bits here. So, I am saving 5 bits for A. Of course, I will have to compensate elsewhere,
C and D, which are
right?
ones.
C and D, यहाँ पे 2 bits थे, यहाँ पे 3 थे, but C and D occur very infrequently, so it's good, right? So this will have less than 29,
Saving on R also.
right? We are also compensating on R. No, R is in the right direction, right? R is
We are saving on R.
we are saving on R, yeah. So this you can check will require 24 bits. Okay. So we have to design this in such a manner so that the number of bits required is as little as possible. Okay. Is that clear to everyone? Good. So let's try and understand. So what is it that we are given? We are given the frequencies of the characters. So suppose I give you a piece of text, you will count the frequencies of the characters. Frequency means how many times each character appears. And we are trying to compute a trie so that the length of the encoding we get is as small as possible. Recall that each character is a leaf in our trie. Okay. Number of bits used to encode a character is its level number. Yes, where I am assuming that the root is numbered 0. Yes. So if the ith character has a frequency of f sub I and has a level number of L sub I, then what is it that we are trying to minimize? Summation fi Li. Yes? Everyone understands this? So we have to choose a tree so that this quantity is minimized. Our tree will determine the Li's. Fi's are given to us, right? We cannot change the Fi's. We can pick a tree so that we can get the right Li's, the appropriate Li's. Okay? So this quantity, summation fi Li, is called the total external weighted path length of a tree, right? Should be very easy to see why, right? External, because हम external nodes के ही बारे में बात कर रहे हैं, which are our leaves. उनकी path length क्या हुई? The length of the path from the root to the leaf, which is basically the number of levels. Weighted, why weighted? Because we are multiplying it by the frequencies. And why total? Because we are summing it up, right? So we are viewing each leaf as having a weight which is equal to the frequency of the corresponding character, right? The weights in this weighted correspond are referring to these frequencies fi, right? So sometimes I might call, from now on I might call the same thing as weight or frequency, right? Don't get confused, it's the same thing. So here for instance I write, so given these weights or frequencies f1 through fn, we wish to find a tree whose weighted, total weighted external path length is minimum. Right? That is what we want to do. We are given the weights on the leaves. We want to build a tree whose leaves will be these and whose weighted external path length will be minimum. And we will denote this minimum weighted external path length by this quantity. Right? So given n leaves with weights f1, f2, f3, fn, right? Build a tree. Your problem is build a tree, a binary tree, right? Whose leaves will be these n leaves, and which will have the minimum weighted external path length, total weighted external path length, right? So we have managed to translate our question of finding the minimum length, an encoding such that the length of the our encoded message is minimum, to that of designing an appropriate tree, right? Okay, one thing I am going to assume is that when I write it in this way, f1 is smaller than f2, right? These are in increasing order. Okay, so now let me show you what the algorithm is. So once again my text is the same, abracadabra. There are 5 characters and I have put down the frequency of these 5 characters. Right? At the very first step, what I am going to do, so I have put red boxes around them. These will have to be the leaves of my tree. Right? Now what I am going to do at the very first step is I am going to take the 2 with the smallest value, which are the ones and the ones, right? These are the two smallest ones, and I am going to combine them. How am I going to combine them? I am going to create another node. So, I am building up the tree now, right? These are my leaves. So, I make another node as the parent of these two, and this node gets a value of a weight of the sum of these two. Okay? And now these two will disappear from the picture, and I will just be left with 4 nodes, and I will repeat the process on them. So, what is the process? Take the two smallest
Add the frequencies and make them combine them together into a node.
And combine them together into a node. Take the two smallest and combine them together into a node, and when you combine, you basically sum up their weights. So, at the next step, we have an option. We can either combine B and R, or we can combine R with this one that we just created. Let us see which one I take. I decide B and R to be combined into one. Right? When you have an option, you can pick whichever you feel like. Right? So, they have combined into one, and now I am left with only 3 nodes. ठीक है? कितनी बार मुझे ये काम करना पड़ेगा? How many times will I have to do this process? If I started off with n leaves, how many times will I have to do this process? n by 2? Every time you are reducing a node by 1. Yes? तो कितने times करना होगा? n minus 1 times. ठीक है? Not n by 2 but n minus 1 times. Exactly. There's no, right? Now which will we combine? 2 and 4 clearly, right? Because they are the two smallest ones. So we combine them into one, we get a 6, and then finally we have only 2 nodes left, 5 and 6, so they will get combined. This is the picture. We'll combine them into one, and this is 11, right? And now how do I label? I can just label whichever way I like. It really does not make a difference. देखिए, length of the encoding was not determined by ये 0 है या 1 है. It was determined by the depth of this thing. So एक तरफ आप 0 लेबल कर दीजिए, एक तरफ आप 1 लेबल कर दीजिए. ठीक है? So this becomes my encoding now, right? And the claim is that this is the best. This will give you the same minimum, right? Whatever was the minimum for abracadabra will be achieved by this. As you can see, A, which was occurring 5 times, is getting only 1 bit. Yeah? So looks like it's doing the right thing. Okay, so this is our final try. This is my text. This is the corresponding code. As you can see, for A you have 0, for B you have 1 0 0, so next 3 characters. For R you have 1 0 1, the next 3. For C you have, for A you have a 0, for C you have 3, and so on and on. There should be a gap between this 1 0 1 and 0 because this A corresponds to last, and these are only 23 bits. Right? This is even better than the previous code I had shown you, which was 24, and this is the best possible, which is what we will argue in this class. कि आप इससे better कर ही नहीं सकते. ठीक है?
सर लेवल 2 और 3 उसमें खाली छूट गए थे.
किसमें?
इस वाले में लेवल लाइक लेवल 1 एंड 2 ऑन द राइट साइड, वहाँ पे बी और सी डी अगर एडजस्ट हो जाता तो मे बी इट कुड हैव बीन इवन बेटर.
सी यहाँ एडजस्ट हो जाता तो किसी तरह.
हाँ मतलब अगर होता, मतलब यू आर सेइंग दिस इज द बेस्ट पॉसिबल.
तो नहीं हो सकता है.
नहीं हो सकता.
ठीक है? Let's see, we can maybe, so let me take another example, and let me take the same example and then build another try, right? Why will how can I build another try? You recall that there was an option at each point. Let me take the other side of the option. Let me see what try I get now, right? So यहाँ पे minimum 2 थे, अब मेरे पास यहाँ 3 2s हैं. तो पहले मैंने इन दोनों को combine किया था, मैं इन दोनों को भी कर सकता हूँ. So let me do that. I decide to combine R with this one, and I get a 4. Right? Now which I have to combine? This 4 with this 2. So I combine the, okay, now I am doing that. Combine the 4 and the 2, and then I get 6, and finally I am going to combine this and this. Right? So this is the final try I get. Right? और भी अजीब सा लग रही है. बहुत सारे एडजस्ट करने की पॉसिबिलिटीज लग रही है यहाँ पे. Let's see. This is the final try. Same piece of text. Once again, A gets only one bit, B gets 2, R gets 3, A gets 1, C gets 4 now, and D also gets 4. Right? Do you think it will be different from 23? No. It should not be, right? Otherwise, the theorem I am claiming is false, right? It should be the same. You can count, it will be 23. Okay? Because this algorithm is computing the tree with the minimum weighted external path length, right? And since it's the minimum, it cannot be smaller than the other one or larger than the other one, because they are both the minimum. Okay? So, we now need to argue correctness. Why is this computing the minimum? Who said it's computing the minimum? So, why does this algorithm compute a tree with the minimum weighted external path length? Right? There is no reason to believe, it is too simple to do anything useful. Right? So, let us see what the argument for this will be. We will be proving it by using induction on the number of leaves, which is the same as the number of characters. Right? So, suppose I gave you only 2 leaves, then what is this algorithm going to do? It will just combine them into one, and so it will basically give you a tree with the 3 nodes, one root, and this will be 0 and this will be 1, and this will be something and this will be something, and clearly it is using 1 bit for each of the character. You cannot do better, right? You cannot take 0 bits for a character. Okay? So, it is true for when you have only 2 leaves. So, we are going to assume that the claim is true when you have n minus 1 characters or leaves, and we are going to show that it is going to be true when you have n characters or leaves. So, when we have n characters, what are we doing at the very first step? We are taking the 2 characters with the smallest frequencies and combining them into one, so to say. Right? We are taking the 2 characters with frequencies f1 and f2, and we are replacing it with one node of weight f1 plus f2. It is as if you have one character now of frequency f1 plus f2. Right? So, once it does that, beyond this point, the behavior is as if it was given n minus 1 characters with frequencies as f1 plus f2, f3, f4, f5, f2, fn. Right? Beyond that point, it is the same behavior. So, beyond the point, the algorithm behaves as if it had only n minus 1 characters with frequencies f1 plus f2, f3, fn, all the way up to fn. And so, using our induction hypothesis, it would have computed the best possible tree over these, because these are only n minus 1 characters now, and it would have computed a tree on these n minus 1 characters with total weighted external path length as this quantity. Right? This was the minimum quantity, this was the notation we used for the minimum. Right? कुछ confusing सा हो गया यहाँ पे, क्या confusing हो गया? नहीं तो वो तो आप ऑर्डर चेंज कर दो यहाँ पे, तो नंबर्स तो वही है ना. ठीक है, तो इसने जो है, तो आपने क्या किया, आपने पहले जो 2 f1 f2 वाले थे इनको कंबाइन किया इनटू 1, इसको नाम दे दिया f1 प्लस f2, इसको वेट दे दिया f1 प्लस f2. इसके आगे जब एल्गोरिथम प्रोसीड किया तो इट कंप्यूटेड सम ट्री. इस ट्री का, ये वाला जो ट्री उसने कंप्यूट किया है, इसका टोटल वेटेड एक्सटर्नल पाथ लेंथ इस क्वांटिटी के बराबर है. किसका? इस ट्री का. तो पूरे ट्री का कितना हो गया टोटल वेटेड एक्सटर्नल पाथ लेंथ? देखिए, इस ट्री का, ये वाला जो है, ये वाले ट्री का टोटल वेटेड एक्सटर्नल पाथ लेंथ इतना है बाय इंडक्शन हाइपोथेसिस. तो इस पूरे ट्री का टोटल वेटेड एक्सटर्नल पाथ लेंथ कितना हो गया? कौन बता सकता है? देखिए, बाकी जो नोड्स थे उनका तो लेवल नंबर कोई चेंज नहीं हुआ है ना। हमने इस क्वांटिटी में इस नंबर को f1 प्लस f2 को इस लेंथ से मल्टीप्लाई कर रखा है, जो भी इसका पाथ लेंथ है। मान लीजिए इसका पाथ लेंथ x है, तो हमने इस सम के अंदर f1 प्लस f2 इंटू x कर रखा है काउंट, और जबकि पूरे में हमें क्या काउंट करना है, f1 इंटू x प्लस 1 प्लस f2 इंटू x प्लस 1. So how much is this different from this? By f1 plus f2. Great. So the tree computed by this algorithm has weighted external path length f1 plus f2 plus this quantity. Right? So this is what our tree has computed. Our algorithm has computed. This is the weighted external path length computed by this Huffman's algorithm. Okay. Now we have to argue that this is the minimum possible. इससे कम नहीं हो सकता. ठीक है? What we'll argue is that the best solution for f1 through fn equals f1 plus f2 plus exactly this quantity that our algorithm had computed. We'll argue this now. Right? That this quantity that our algorithm has computed is actually the best, is the minimum weighted external path length when your weights were f1 through fn. या ये समझ में आ रहा है? अब ये हमें आर्ग्यू करना है, तो इसको कैसे आर्ग्यू करेंगे? Okay, this will follow from the fact that in the optimum tree, by the optimum tree I mean the tree जिसके लिए weighted external path length आपका सबसे कम है, उसके अंदर जो दो सबसे छोटे weights हैं वो siblings होंगे हमेशा. Okay, let's prove this fact. Okay, let's say how does this, so suppose this fact is true, how does this imply this?
So
Why does this imply this?
WETL,
they have to be at the lowest level to which sibling नहीं बचेगा.
So we are creating the tree.
Okay,
in such a
no,
way
so we are going to do, let's do it one step at a time, right? Let's first argue that this implies this, right? Suppose we had proved this fact that in the best possible tree, suppose we had proved that in the best possible tree, the two lowest weights are siblings.
Because every time we are increasing the levels of these two siblings, so if they were not the lowest, then the number of bits would be more than the minimum required from.
Right. So we'll do that in slightly more formal way. Right. So let's assume that they are siblings. The two minimum are always siblings. Let's argue that if this is true, then it implies this. Right. So we have the best possible tree, और जो दो minimum हैं, they are siblings.
सर ये तो हमने माना ही था when we were
वही तो.
ये तो रूल में था, बट ऐसा जरूरी, हम यही तो आर्ग्यू कर रहे हैं कि हमारा रूल बेस्ट है, बट ऐसा जरूरी नहीं है, राइट? तो अब ये हम प्रूव करेंगे कि ये बेस्ट ट्री में हमेशा ऐसा होगा कि जो दो मिनिमम होंगे वो सिबलिंग्स होंगे, विच मीन्स उनका पेरेंट एक होगा. ये अब हम प्रूव करेंगे. पर अगर हम इसको प्रूव कर देते हैं, व्हाई डज इट इंप्लाई दैट वी हैव फाउंड द बेस्ट? Because it implies this, that the best over f1 through fn equals this. Why? This is the best tree. The best tree मतलब इसका weighted external path length सबसे कम है, और f1 f2 जो हैं वो siblings हैं, जो leaves जिनका weight f1 f2 है वो siblings हैं. ठीक है? अब हम क्या करेंगे? अब हम बाकी का ट्री देखेंगे.
In this case, when we are proving what are we assuming exactly?
We are going from here to here, which means that we have assumed this statement and we are proving that the best tree over f1 through fn has weighted external path length equal to f1 plus f2 plus the best tree, the weighted external path length of the best tree over f1 plus f2 through fn. Right? So now we are kind of trying to mimic what we've already done. Let me now look at this tree. Okay? So for this entire tree, iska weighted external. Okay. Now let me. I'm just looking at the remaining tree. This is a tree, and let me give this node a weight equal to f1 plus f2. Right? Now this is a tree over leaves f1 plus f2, f3 up to fn. Right? इसका weighted external path length क्या होगा? क्लेम है इसका weighted external path length minimum possible होगा इन सब के लिए. अगर ये पूरा बेस्ट ट्री था फॉर द एंटायर थिंग, तो इन लीव्स के लिए, इन वैल्यूज के लिए दिस शुड बी द बेस्ट ट्री. डू यू फॉलो व्हाई?
By induction.
No, not by induction. देखिए we are now looking at the best tree for f1 through fn. We are looking at the best tree for f1 through fn. Okay, I am saying the following. Let's cut off the two leaves and just keep that. Then and give this a weight of f1 plus f2. Then this tree is the best tree for these choice of weights also. Why? Suppose it was not. Suppose there was something smaller possible.
Then it would have been incorporated in the previous one.
Then this blue one would not have been the best tree for these guys. Why? Suppose ये वाला red जो है best tree नहीं था, एक green था best tree. Sorry, I should draw green. Okay, let me now draw in green. Suppose हाँ rubber हो रहा है. Great. Suppose there was a green tree which was the best tree. And तो best tree है तो उसकी एक leaf जो है f1 plus f2 है. ये वाली ये green से दिख नहीं रहा है. So I don't seem to have a good collection of colors here.
Black use करते हैं.
मैं black ही use करता हूँ.
You use red, we'll assume it to be green.
Okay, let me use black only then. I still have to learn how. Right? So suppose this black tree was the best. Better than this red one. तो अब इसका मतलब इसका weighted external path length इस black tree का इस red tree के से कम है. अब मैं क्या करूंगा, ये जो नोड जिसका f1 plus f2 था, इसके दो चिल्ड्रन बना दूंगा, f1 and f2. राइट? तो इसका मतलब अब ये जो ट्री मैंने बनाया है, इसका वेटेड एक्सटर्नल पाथ लेंथ ये ब्लू वाले से कम हो गया. नहीं समझ में आया? देखिए, लेट मी रिपीट द आर्ग्यूमेंट. ध्यान से सुनिए. हमारे पास ये ब्लू वाला ट्री था जो आपने कहा कि बेस्ट ट्री है. ठीक है? इस फैक्ट से कि बेस्ट ट्री के f1 और f2 जो है सिबलिंग्स होंगे बेस्ट ट्री में, राइट? तो इसका मतलब f1 f2 बगल बगल है, तो उनका एक पेरेंट है. हमने ये दोनों हटा दिए और f1 प्लस f2 इसको नाम दे दिया. अब हमारे पास कितनी लीव्स बची? n-1 लीव्स बची. हमने कहा कि यही जो ट्री था ब्लू ट्री, जो बाकी बचा उसको हमने रेड कलर कर दिया. इस ट्री को उसको रेड नाम दे दिया. दिस ट्री इज द बेस्ट पॉसिबल ट्री when you have leaves with weights f1 plus f2, f3, f4, f5, f6. This is the best possible tree. Right? आप कह रहे नहीं, ऐसा नहीं है. अगर ये वाले weights होंगे हमारे तो ये एक black tree है जो better है. तो मैंने कहा ठीक है, चलिए मैं आपका black tree लेता हूं. इसमें जो नोड f1 plus f2 जिसका weight है उसके मैं दो चिल्ड्रन बना देता हूं, f1 और f2. अब ये ट्री जो है इन्हीं लीव्स के ऊपर हो गया, f1 f2 f1 लीव्स पर हो गया. ठीक है? क्योंकि f3 to fn तो ऑलरेडी लीव्स हैं इसमें, f1 f2 और आ गए. अब इसका जो है टोटल वेटेड एक्सटर्नल पाथ लेंथ इस ब्लू वाले से कम हो गया. कम हुआ कि नहीं? देखिए, ये ब्लैक वाले का इस रेड वाले से कम था, और ब्लू और रेड कितने में डिफर कर रहे हैं? f1 प्लस f2 में. और ये ब्लैक और ये जो मैंने अब ऐड किया ये कितने में डिफर कर रहे हैं? f1 प्लस f2 में. तो अगर ये ब्लैक जो है रेड से कम था, तो ये जो नया ब्लैक बना ये भी ब्लू से कम हो गया. पर ब्लू तो मिनिमम पॉसिबल था, तो कोई इससे कम कैसे हो सकता है? ठीक है? तो इसका मतलब क्या हुआ? ये रेड जो था ये भी बेस्ट पॉसिबल था व्हेन यू हैड लीव्स एज f1 प्लस f2, f3 to fn. So this red ka weighted external path length is this quantity then. And so blue ka total weighted external path length is red ka weighted external path length plus F1 plus F2. So which means blue ka weighted external path length, which is this leaves, is equal to this one. And हमारे पिछले algorithm से क्या आया? Exactly यही आया right hand side, right? Which is equal to the best possible. So our algorithm is computing the best possible. This would be right. So if this black is better than the red, then what have I done? I have only increased the black by a quantity equal to F1 plus F2. While this blue also differs from the red in only this quantity F1 plus F2. So if this black is better than this red, then this bigger black is also better than the bigger blue, which violates our optimality. Okay? So this statement here implies this. But why is this statement true? Why should it be the case that in the optimum tree, the leaves with the two lowest frequencies are siblings? Why should this be true?
Because we need to minimize F1 plus F2.
Why should it be true that the leaves with the two lowest weight should be siblings?
They should be having the maximum path length.
Okay, what can you say about, yeah, good. So they should be at the,
Having the maximum path length.
let's take the leaf with the lowest weight. It will have the maximum level number. Suppose this बीच में आ रही है कहीं leaf with the lowest weight, ठीक है, और उसके नीचे कोई और leaf है with a higher weight जो उसके नीचे है. This is not optimum. Why? क्योंकि हम इन दोनों को swap कर सकते हैं.
इससे कम हो जाएगा.
उससे कम हो जाएगा total weighted external path length. तो इसका मतलब the leaf with the smallest weight has to be at the last level. So the leaf with the smallest weight is at the last level. Let's look at its parent and let's look at its sibling. Which is this leaf? By the same argument, this leaf is the leaf with the second largest weight, second smallest weight, sorry. Because if it were anything else, then once again you can swap and reduce. Right? So the leaves with the two smallest weights are actually at the very last level. In all our examples, you must have seen that happening. They are all at the last level, and they have the, and they are siblings. They are at the last level, so they have to be, yeah, they are siblings. Okay? And so the entire algorithm works correctly. It just uses that fact, makes them siblings, and then the problem reduces by 1, because now you have only n-1 nodes to worry about. And how do you take care of the n-1 nodes? In the same way as you took care of them. Once again you take the two smallest one, make them siblings, and continue. So just this one property is being exploited in the algorithm. You get a very simple algorithm to compute the best possible try. Okay, so with that I am going to stop today's class. After we have done priority queues, we are going to analyze this particular algorithm to compute its running time. Right? So I am leaving the bit about computing its running time today, and I will take it up after we have developed the notion of priority.